Hello there. I've got some practice questions for the exam. How many do we have? One, two, three, four, five. Five practice questions. I highly recommend that you try them yourself before you watch this video where I explain the answers and the explanations behind those answers. People learn from their mistakes more than just kind of passively absorbing the information. And um, the material is going to go through everything from chapter 1 to chapter 6. It is cumulative. I can't help it because everything that we cover later in the course necessarily involves material covered at the beginning of the course. It's a inherently cumulative topic. So I recommend rereading and restudying previous material going into the second exam, because the earliest material really is the bedrock foundation for everything that comes after. You can't really build on that foundation if the foundation is shaky. Anyway, here's our first practice question. Each of these scatter plots represents a correlation between two continuous variables. If I told you one of them has a correlation of positive 0.4, which one of the scatter plots most likely correspond to that correlation? Well, right away, you can discount the middle one because it's a positive correlation. If it's a positive correlation, y goes up as x goes up. They should be going in an upward, rightward kind of diagonal direction. They should not be going, when you read left to right, everything should be going up. This one, you read left to right, everything's going down. There's a negative correlation. So it can't be that middle one. Now I said there's a 0.4 correlation. It comes to either this one at the top or this one at the bottom. This one at the top is very close to being a straight line. So what I call a cloudy line. This would be a correlation that's in the 0.8, 0.9 territory. It's very close to being a straight line. Whereas this one is so cloudy that you can almost kind of barely tell that there's kind of an upward trend as you read from left to right. As x increases, y also increases. So this would be the best answer, the first one. There is a moderate positive correlation. This correlation is positive, but it's too strong to be 0.4. So if you had to pick between these, it would be this top one. Here's our next question. I'm doing an independent samples t-test. That's when you have two sample means from two different groups. You want to test whether they're statistically significantly different from each other. I observe a difference between groups of 2.33 with a 95% confidence interval of 1.88 to 2.78. So I saw a difference of 2.33, but it could have been as low as 1.88 or as high as 2.78. Notice that the lower boundary and the upper boundary of the 95% confidence interval are both positive numbers. So you can be pretty sure that there's not an absence of a difference, because if there was an absence of a difference, if there's no difference, then 0 would be somewhere in the interval. Like if one of these numbers was positive and the other one was negative, that means 0 is one of the plausible values that there could be, but there's not. From this information, I can conclude that you can't conclude anything about the data being skewed or not skewed. Can't conclude anything about the data being bimodal. It comes down to the null hypothesis. The null hypothesis in a independent samples t-test is that there's no difference between groups, but I observed a difference so large that 0 is not even really in the realm of probability. So we would reject the null hypothesis. So D, the null hypothesis is probably false. is the correct answer. The next one is Dr. Bell has 20 different variables. So like height, weight, GPA, so on and so forth for, there's 20 variables. I didn't say how many observations of each variable, but imagine you grab a bunch of people at random and you measure 20 different aspects of them. He decides to start testing pairs of variables to see if any of them are different from each other. So you have 20 variables to pick from. You can go and do statistical tests on each and every one and keep looking for something that's statistically significantly different. He does this until one of the pairs shows a statistically significant difference. Dr. LaCour sneers at this and says, well, something's going wrong here. When you take one data set and you keep doing test after test after test, waiting for something to come out statistically significant, we call that increasing the family-wise error rate. Just a quick refresher, a family-wise error rate, when you're doing one test on your data, you have a 5% chance of making a type 1 error. Type 1 error is when you reject the null hypothesis, but you shouldn't have rejected the null hypothesis. If you do multiple tests on the same data, you're increasing your probability from 5% to a higher percent. So if there's really nothing there and the null hypothesis is true, you keep raising the probability that you're going to end up rejecting the null hypothesis when you shouldn't have. That's increasing the family-wise error rate. Statistical power doesn't really come into this because statistical power has to do with sample size and effect size. The bigger the sample, the more statistical power you have. The larger the effect that you're trying to detect, the more statistical power you have. But we don't really have that kind of information here. You're making the sampling distribution too dispersed. I don't even know how you could connect those. You are raising your sample size too much. There's no information about the sample size, just 20 different variables. So D is the right way to go with this one. Got two more. The Census Bureau has sent someone to your house. The man says that they know the number of occupants in each household in the United States. The average is 2.33 with a standard deviation of 0.33. So that means that they know the population mean and the population standard deviation. The population average number of people in the house for all households in the US is 2.33 people and 0.33 standard deviation. That means that 70% of households have between 2 people and 2.66 people in the house. He asks how many people live in your house. You shrug and say 56. Why? The man starts doing some calculations to determine if the number of people living in your household is unusual. What is the most likely analysis he is conducting? The crucial thing here is that this person wants to know if you, a single individual or a single household, has a lot of people in their household, which, 56, obviously, if the mean is 2.33 and standard deviation is 33, I mean, that's a lot. So, but he's not doing a group of households. If the Census Bureau person was going to a neighborhood where they suspect that most houses in this neighborhood have more people living in it than average, then they could do a sample mean. But here we're looking at one person or one score. So this would be a single observation Z-score. And I don't have the option to do a group Z test. But just to help you learn the difference, a group z-test would be used if you like visited a bunch of specific houses from a specific neighborhood or a type of house and got a sample mean of how many people live in those houses, and then compared that sample mean to the population mean. So let's see, 2.36. So let's do, I'm just curious. 56 minus 2.33. So if you really had a house with 56 people in it, that's 53.67 more people than the average, but you turn that into standard deviation units. So you divide the difference by 0.33. That means you're 162 standard deviations above the mean. And if the number of occupants in a house is normally distributed, I promise you that it's not, but in this made up example, that would mean, 4 people in your house would put you in like the top 1%. Not 4 people in your house, 4 standard deviations above the mean would put you at the top 1%. So like, yeah, this is an extraordinarily high z-score. So the guy really wouldn't need to calculate a z-score. It wouldn't be a repeated measures t-test. We haven't even covered that yet. A repeated measures t-test is when you have 2 sample means, but both means are coming from the same group of people. So like a before and after score. So each person contributes 2 observations. One sample t-test is when you want to compare a sample mean to a population mean, and you don't know the population standard deviation, but we have that right here, so it can't be that. And an ANOVA is for when you want to compare 3 or more sample means and determine whether any of them are statistically different from one another. And that wouldn't really fit this situation. All right, last one. Here are 2 ANOVA tables. If you've read chapter 6 and you've watched the chapter 6 lecture video, you should know what an ANOVA table is. In one of these tables, there was a larger percentage of variance accounted for by the between group effect. Which was it? What does that mean? When you have 3 or more means, what you look for in an analysis of variance essentially is how much, so the dependent variable is all over the place. Are you any better off if you want to try and predict where someone is on the dependent variable? Let's use depression scores. People are all over the place in depression scores. Let's say you have 3 samples, 3 different groups of people with different average depression scores in that group. Are you better off, if you want to predict someone's depression score, are you any better off knowing which group they came from, or does it not really make much of a difference? And you just predict the overall average. If an ANOVA is statistically significant, and both of these are, the p value in both of them is 0.001 or less than 0.001, that would mean that actually knowing what group they came from would help you make more accurate predictions, which correspondingly means there's enough of a difference among the groups that there's added information. Knowing which group someone came from gives you added information that is useful in making predictions. So which one does this to a greater extent? Which one accounts for more variance with the between groups effect? Well, there's 1,000 overall variance in the top one, and about 1/3 of that 1,000 is accounted for by the difference between the group means. And about 2/3 is left over, which has gone unaccounted for. So this residual means leftover. Look down here, and you have about 60% is, so the total variation is 500. This is the total is, this is how much you could possibly have. This is like the total accuracy you could have had in making predictions. 333 out of 500 is, roughly 60, unless I'm having a complete brain fart. 20, 40, 60. It's a little over 60. A little over 60% compared to 1/3 over here. So table B has a higher proportion of the total variance being accounted for. Up here, 1/3 of the total variance is being accounted for by the between groups effect. And over here, about 60% of the between groups effect is being accounted for. 333 out of 500. So the correct answer is B. I think it's clear why A is wrong, but they actually have the same percentage of variance accounted for by the between group effect. Your question lied to me. That's a lie. They don't have the same proportion. This one's like 33 1/3%. This one's like 60%. There's actually not enough information presented in the tables to answer the question. No, there is enough information and we've gone over it. So that's a little preview of what kind of questions you can expect on the second exam. Hopefully this helped. If any of this is not making sense, please feel free to contact me. I'm willing to go above and beyond to try and clear up any of this stuff. I'll make extra videos. Shoot me all your questions and good luck on the exam.